So today we'll see what is the concept behind the sampling theorem or the Nyquist theorem, how it was invented, and what is the basic behind that. So for that, just let us consider a cosine signal. This is a cosine signal. The blue is a cosine signal. Assume that you are drawing this signal on a paper. When you are drawing the signal on a paper, it is simply that you are drawing the infinite number of points. Okay, any signal, if you are considering the cosine, sine, triangular, any signal, if you are considering, you will be drawing the infinite number of points. So we will first see what is the need of sampling. So whenever you are generating such signals in any digital systems like MATLAB or any mobile phones or any computers or any digital system, you need to have some finite number of points. You cannot draw or you cannot have the infinite number of points. So to have the infinite number of points, you must have the samples of this actual continuous signal. So that is the basic behind the sampling. Now, you cannot sample the signal as per your wish. You must satisfy few rules whenever you are sampling the signal. So that rule is called as sampling theorem or Nyquist theorem. So let us see the Nyquist theorem in some other aspect. If you would have referred many videos about the Nyquist theorem sampling theorem, but in this video we will be uh, considering or understanding the Nyquist theorem with some other aspect or some other angle, which is somewhat easier than other. So consider some signal in time domain. There is some signal in time domain which will be looking like this in frequency domain. There is some signal in time domain which will be looking something like this in frequency domain, which has highest frequency component of FM. That is, it is ranging from minus FM to plus FM. The spectral width of this signal is minus 2 FM. Spectral width is 2 FM and the bandwidth is FM. Bandwidth is always one-sided. Now, when you sample the signal in time domain, it is simply the multiplication with impulses in time domain or is simply the convolution with impulses in frequency domain. Means this signal is convolved with impulses in frequency domain. So, or if you do not understand much about the convolution and multiplication, simply consider whenever you are sampling a signal in time domain, it repeats in frequency domain. The spectrum repeats in a frequency domain. Okay, this is a repetition of the spectrum. Now, whenever the spectrum is repeating, you must take care about the fact that this must not overlap with the next one. This should not overlap with the next one. If you do not want this overlap, the separation between this center and this center should be at least 2 FM. The separation between these two should be 2 FM because this half part is FM, this half part is FM. The separation should be at least twice of FM. So this is the basic behind the Nyquist theorem. What Nyquist theorem states that whenever you are sampling any signal, the sampling frequency must be at least 2 times the signal frequency. The sampling frequency should be at least 2 times the signal frequency to achieve the proper spacing between the two spectrum samples. Now in this case, there is no separation between these two. When one ends, the another one starts. So let us see what happens if you are sampling below the uh, Nyquist rate or 2 FM. So this is the case. So if you can consider here, we are sampling the signal with the frequency which is equal to the again signal frequency. We are sampling with a frequency FM, not 2 FM. So in this case, this overlaps with the next one, this overlaps with the next one, this overlaps with the next one. The separation between the two centers is only FM. The separation between the two centers is only FM. In such cases, whenever you are doing this, for human eye here in this figure, you can distinguish between these two. But practically, it cannot distinguish whenever it is a DSP system because this forms a resultant between these two. Whenever it is overlapping, it forms a resultant between these two. What is the resultant is up to this point the signal is rising. So this point it is rising. At this point it is falling. The another signal is rising. It adds both of them because these are overlapping. The falling one is added with the rising one. You get a constant line. Again at this point it is same. The rising one is added with the falling one. You will get a constant line, and so on. In a frequency domain, you will be getting a constant line, and at the end or last sample, you will be getting a falling line. So this is what happens whenever you are sampling the signal with the FM. This is all in a frequency domain. But what happens in time domain? Whenever you are sampling with the frequency equal to signal frequency, you will be getting a DC in time domain after reconstruction of a sampled signal. How? We will see it later. But just assume or understand or remember, you will be getting a DC in time domain whenever you are sampling with frequency equal to signal frequency. Now let us consider what happens if you are sampling with the frequency which is higher than the Nyquist rate. In this case, you are sampling with a frequency which is even more than 2 FM. So it's okay because your spacing between the two nearby spectrum samples is uh, even higher than 2 FM, or the centers are spaced with frequency which is higher than 2 FM, which is okay, acceptable, because you can distinguish between the two successive or two nearby spectrum samples. This is called as oversampling, which is always preferred whenever you are sampling any signal. Now let us consider what happens in time domain. So this is a cosine signal, as I told you. So as the Nyquist theorem states, you must sample with a frequency which is at least 2 times the signal frequency. Many people do not understand its meaning, what happens in time domain. In time domain, it means you should create at least 2 samples per one cycle. Twice frequency means 2 samples per one cycle of the original signal. So here I am creating one sample in a negative cycle, another sample in positive cycle, again one sample in negative cycle, next sample in positive cycle, so that we are getting 2 samples per cycle. So this is the sample signal. Now this signal is assumed transmitted in a communication channel on a communication channel. So at a receiver, we receive the same sample signal. Now receiver tries to reconstruct the original signal. So whenever it tries to reconstruct the original signal, so what it does is it simply joins the two nearby points or two successive points. Whenever it is joining the two successive points, it may follow some pattern or it may follow simple linear pattern. So here, if you're connecting with a line or following a linear pattern, it's simply like, sorry, this simply likes a triangular wave. So you are transmitting a cosine signal or sampled version of a cosine signal and having only 2 samples per cycle. You're sampling with an Nyquist rate. At receiver, it is reconstructed as a triangular wave. So remember, whenever you are sampling with Nyquist rate or exactly with a Nyquist rate, the shape of the signal may not be guaranteed, might not be guaranteed. However, the frequency of this triangular wave is same as that of the frequency of this cosine wave. The shape is different, however, the frequency is same. So if you are sampling with a Nyquist rate, you may not get exact shape of the reconstructed signal, however, the frequency will be same. That is one thing. Now let us see what happens or the cases where your Nyquist theorem may fail if you are not taking the precaution during sampling. Consider the same cosine signal. You are taking the first sample here at 0 volt. Next sample is again taken here at again 0 volt. At equal intervals, you will be taking the samples. So you are taking samples. You are sampling with Nyquist rate. You are taking 2 samples per cycle, 2 samples per cycle. However, all samples are taken at 0 volts. So this is how the sample signal will look like. So in this case, your all samples are of 0 volt samples. So you are transmitting this signal, it will be reconstructed receiver. Receiver will think that you are transmitting the 0 volt samples. So receiver will reconstruct a 0 volts, 0 frequency signal. Means nothing. A 0 volt, 0 frequency signal means nothing. You have actually the cosine signal which is sampled with an Nyquist rate. Still you are not able to recover your original signal because you are missing the or you are making some mistake while uh, taking the samples. You must take care about the position of the first sample basically, or the position of the samples. You should not sample the 0 volt samples. So even if you are satisfying the Nyquist criteria, you may not be able to recover the original signal at all. So to avoid such cases, the precaution needs to be taken. You should sample any signal with frequency which is at least 10 times higher than your signal frequency. At least 10 times higher than your signal frequency, so that you can reconstruct a proper shape of your original signal and you should not get such 0 volt concept or 0 volt signal at the receiver. Now let us see what happens if you are sampling with the frequency which is equal to the signal frequency. So in this figure, as I told you, you are sampling with the frequency which is equal to the signal frequency, that is FM. Your samples are overlapping, as I told you. So what happens in a time domain is, if you consider the cosine signal, same cosine signal, you are sampling with signal frequency, not Nyquist frequency. Means you are taking one sample per cycle. Practically, you should take two samples per cycle to satisfy Nyquist criteria, but here you are taking one sample per cycle. So what happens is, in this case, let us consider we are taking only the samples in positive half cycle. So you'll be getting only this part of the signal, only the upper part. So in a sample case, you'll be getting only the upper part of the signal. So it is just positive impulses that will be transmitted through the communication channel, and at a receiver, it is reconstructed just by joining all these impulses. When you join all these impulses, you will be getting a straight line. Now receiver assumes that your transmitted signal was a simple DC straight line with a peak voltage of whatever the voltage of these impulses is. Again, I repeat, receiver will be getting only these positive impulses if you're sampling with the signal frequency that is equal to FM. The receiver will simply join these signals. You'll be getting a constant flat line. A constant flat line in time domain means it is a DC. When your actual signal is your cosine signal, you have sampled with signal frequency. So remember the new concept, or one more concept is, whenever you are sampling the signal with its own frequency, you will be getting a DC after reconstruction. Therefore, you must satisfy this Nyquist criteria, or even if you want to get, or further, if you go ahead of this, if you want to get exact shape of your transmitted signal, and you should, if you want to avoid the 0 volt sample getting samples, or get 0 volts getting sampled, you must sample the signal with frequency which is at least 10 times of your signal frequency. So it should be obviously higher than your Nyquist rate. It will be higher than your Nyquist rate. So sample with at least 10 times higher than your signal frequency. I hope you understood this concept. So this is the basic behind your Nyquist theorem or sampling theorem. So I will be uploading few videos which will be indicating how the Nyquist theorem is applicable for human eye, how it is applicable for regular cameras, uh, and how the human eye uh, creates aliasing if you're not sampling with the Nyquist rate, what will be aliasing and all. But for the basics, this is sufficient. So thank you.